So this is episode 15 of Prologue is Amazing. And today I'm going to talk about object-oriented programming, why I think it's wrong. I'm going to talk about Haskell, why I love Haskell, why, um, but why I want to use Prolog instead. Mostly I've done Haskell programming over the years. And um, I'm going to talk about graph algorithms. I'm going to talk about Steve Scienna, a professor at Stony Brook, who kind of, he, his thoughts are interesting, and so I'm going to talk about a bit about that, and I'm going to talk about a bit about projects I want to do, some kind of things I want to do. So, beginning with object-oriented programming. Now, object-oriented programming, there's a beautiful vision that comes from Alan Kay, where basically he was trying to describe objects as basically computers, right? So he was like, instead of one computer, you get to have millions of little computers, right? And then the way it works is the computers will just communicate, they'll send messages to each other. So his vision is not about inheritance, right? So if we would take away a lot of the problems with object orientation that people usually say is like these inheritance hierarchies that are a mess. Remove that even. Let's say you program in just the way Alan Kay intended, where you have objects and you send messages to them. You don't even receive messages, right? So it's not like you call an object and you get a message back, or even an object back, a data structure back. No, you just have objects and you can only call a method on them, and you only send stuff to them. So the only way the calling object will ever receive anything back is if that object calls another object, and there's like a chain of objects that come back and do something to this object, right? Like basically it's a forward system. It just chains forward. Uh, the problem is that you have to know the objects. Like, how do you have to connect the objects up somehow. So how do you do that? And so somewhere in the code you have to start. You need references to objects. Now the point of Alan Kay's vision was decoupling, right? And he talks about late binding and things. It's like you want the maximum extent possible for everything to be separated. You don't want things to know about other things. And then you can just put them together as you like. But then how do you do that really? Like it starts to become a problem because yeah, sometimes it works. Like if you have a main object and it has lots of subcomponents, and there's a proper hierarchy that is modeled on the real world, then it all works out fine, right? Like let's say you're modeling a car and it has a steering wheel and it has wheels, and so if there's the car's represented as an object, you send it a message like turn right, and then inside it the data structure turns right, and then the wheels, it turns the little wheel objects that it has references to, they turn right. So it works in that case. But then the problem is, let's say this is a visual object, let's say. Well, how are you getting the results back, right, of all that's going on in the object? Who are you sending the results to? And so when you create, like let's say there's a visualizer object. When you create that object, you're going to have to pass it a reference to the visualizer object, or something inside the object is like there's a visualizer object, right? Or and let's say if it has to interact with other objects, how does it do that? Are you putting the references in that object, or are you sending it somewhere else? Eventually, basically, you start realizing you need some kind of outside layer to send the objects to, or you have to embed all that knowledge into each object. Like you have to pass it references, right? So it's not a decoupled system. If it is, it's basically the only way to decouple that system is to have some kind of central service registry where objects can ask for things or put things into. That's how I would describe it, right? Like people have, they do object oriented, and if you look at it, it's all like none of all the object oriented libraries that I've seen are, they're indecipherable, right? So that's, I think, the essential problem with object orientation. It starts off with the notion of decoupling and, encapsulation, hiding concerns, and ends up realizing that you just cannot do that. So, or if you do that, and it all becomes extremely obfuscated and cold. So, like maybe the right way, like you need registries. You need a source of, let's you end up needing some kind of global registries where maybe these, if you truly want to decouple them, these objects have to ask for things and uh, send messages to a centralized system. And like let's say there's mailboxes. Even then, which mailbox do you send to? So the objects start having to advertise, right? Like it's like a real world economy where it's like, let's say the objects, people are the objects. Well, there's let's say the real economy, there's advertisements, there's stores, and they advertise what they're offering. You have to read the advertisement, or you have to go to the store and pick up what you want. And if you want to send messages and things, so it's, the neat vision is gone, right? And why don't you do it? So that's why I think Prolog is amazing in that sense, right? Because in Prolog, or let's say relational programming, right? Like SQL with a database, with database backed websites. Like I originally got this vision from, I think, Philip Greenspan and database backed websites, and Alex's and Guide to Web Publishing, right? Where he's like, you know, I read this 25 years ago. He's like, object oriented is wrong, and really you want a database and then queries on that, and then really that's all you need. So you can think of it that way. It's like, why put all this data into the little objects, but they still need a centralized some kind of database to query, to communicate with each other. So why don't you just dispense with all of that and just have all the data out in the open? That's Prolog, or that's SQL. You have a bunch of data and you have to query it, right? Now, it like there is a problem. You have to know about the data, and objects seem nice in theory that you can just hide stuff away, and you can be not overwhelmed with complexity. But as we just said, you will be overwhelmed with complexity because, like, where do you hide? Like, you can hide some of away, but when you start to connect them together, there's going to be a central database, right? Now, I am maybe something like a hybrid model where it's like you can have all, maybe you want to start minimizing the amount of data in the database, right? Or because maybe whatever can be encapsulated should be encapsulated behind an object, and maybe like the database should be a central service bus, and right, and the objects hide it. But then why even have the objects, right? Or there's the main criticism or come of object orientation, where you should not put mutable state in all over the place, right? Because you can't, the testing becomes more difficult. You can have bugs in the system, and if there's mutated state everywhere, then it's difficult. So that's the viewpoint from the functional programmers. And the functional programmers have a lot to say about this. Like, they have good things to say, because they're like, well, they start with a conception. Yeah, you have the data out in the open, and you just have functions, and they look over the data, and then you just chain a bunch of functions together to get whatever parts of the data you want, and there's no mutation. And so, how do you, and connecting up things, it also becomes an easy matter, because if you say, well, it almost, becomes an automatic thing oft almost, because you're like, well, here's a function, it takes this kind of data out in, takes puts this type of data out, and then almost like just you can start to chain together functions. You're like, well, I want this data out, this type of data out, and I want this or structure of data out, and this is the data structure that exists. So you just have to write a function that goes from that data structure to this data structure, and then maybe you can do it piece by piece, or you look over all the other data, the functions you have, and what data that comes in and out, and you can just put it together. In fact, theorem provers do it automatically. You just kind of like define a function, what goes in, what goes out, and they might automatically generate the code that does all that. So you don't even have to like do procedural or functional code. You just like, this is the data in, this is the data out, what's the function. So, and like in something like, you can, the way they might do it is, let's say you're making a game in Haskell, like you have one huge data structure, and then you just take pieces and pieces from it, and every iteration in the game, like every new frame, is basically you're taking the global data structure, and then you're creating a whole, like the global game state, and then you're outputting a new game state, right? So there's a game state. This represents all the information about the game, basically all the information that can change about the game, and you have a function that takes that and takes an input from the user, like a keystroke or mouse or whatever, and then outputs another state, right? And so the game is a series of state changes. Like it's just a series of states that have changed by some amount, and that way there's like, you don't, right? Whereas an object-oriented system game would be lots of objects all over the place. They have to communicate. You have to link up how they communicate with each other, and they have immutable states. So you can have lots of bugs in lots of places, and right where, so it is, in that sense, it's like a worse system. A Prolog based game engine might be modeled on the Haskell one, right? It might be, well, here's the data, the state of the game. And given a user input, find the new state of the game. And then and that's the next state of the game. So, because also in Prolog, it's a similar concept. It's like they yeah, like a lot of Prolog programming, they tend to think like same as the functional thinkers, where you want to think in terms of state changes of the global state of the system, like incremental changes, and um, you don't want side effects, right? So you don't want mutation. So um, yeah, so that's my critique of object-oriented programming. And I whenever I've done coding, I've tried object-oriented, and it just seems much less natural to me than functional or relation logic programming. And functional programming often I love. Like I love Haskell. I love that. Like almost like in Haskell in OCaml, I'll define the type. I'll define a data structure, the type, and it's almost automatic the rest because I'm like, well, I want this, and then I've quite easily I'll figure out how to write a function, and the compiler will help you while you're doing that until it's done. And in fact, Haskell and OCaml programmers think every program is basically a compiler. It's a transformation from one thing to another. So you should view every program you make as that. And I'm starting to realize that's how I should think of Prolog too. It's like I haven't done much Prolog programming, but like I always viewed Prolog as as a kind of SQL database. Basically, it's like, well, it's like SQL. It's a bunch of tables, and you have views over them. In Prolog is rules, and you just do that. And but I did a bit, and then I started using lists in Prolog as well, and then started realizing, like it has some similarities to, the functional programming, and then reading more on Power of Prolog from Marcus Triska, started realizing, yeah, you have to start thinking in terms of states, transitions, and so all the kind of knowledge you gain from functional programming is also kind of applies that maybe you should be thinking of your program as a compiler that transforms one thing to another. Now, I haven't really done that much, but I'm looking forward to doing more of that. Now, a thing is, yeah, so the onto the next topic was Steve Skinner. He wrote the Algorithm Design Manual and also the Data Design Manual. Those books are really good. I've almost implicit, without even reading them, I was already thinking along those lines for years, right? Because what he does is he doesn't put maths, he doesn't put theorems and proofs. His books are basically algorithms books, algorithms and data structure books, but they don't have theorems and proofs in them. And I like that because, I don't have a good math background and I don't like doing that. But also, um, he looks for not even too much discussion of the algorithm itself. What he's trying to say is, well, this is this is a kind of algorithm that applies to a problem, like if, and this is what it does, kind of, and if you can map your problem onto this, then you have a ready-made solution, right? And he says it especially for graph algorithms, like graph theory, right? So it's like if you can, you have a problem. If you convert it into a problem that can be solved by a graph algorithm, then your problem's solved. Simple. You just use the pre-made graph algorithms. He doesn't try to, talk about how to refine graph algorithms or even how they work too much, right? And the same is the data science theory one as well. So he's more like the real trick is to figure out how to solve problems using pre-existing algorithms. It's not to get a problem and then figure out an algorithm for the problem, because maybe the algorithm figure out will be slow. And it's not about, like algorithms and like the study of algorithms and how fast and their space and time efficiency, whatever, things like that, and comparing them. So it's more like and he's given interviews and I've read stuff, and it's very interesting. I like the way he kind of has an applications focused outlook. He's even used some of that to like do literally virus design. Like he's uh, like vaccinations. Like he kind of it's a long story, but it's like he used algorithms to figure out. Like he looked at RNA and DNA sequences and how to design proteins using the slowest possible way to create a particular sequence of DNA by using algorithms knowledge, and then maybe graph theory knowledge, and then that was actually used, and it was used to create vaccines, like because it was slower to make that protein by the cells, so then the cells replicated less, so or whatever, the virus replicated less because it was taking longer, so it was a vaccine that worked. Right, so the applications I want to do it's like I want to do something in robotics. Let's say I want robots to make a building. Now, here's the problem, and I want to create an animation of a building being made by robots, and this animation should be detailed. It's not just like a for the visual appearance. Like I actually want a system that builds it, and then this is a visualization of that, right? Now, even the building, I don't want to design it. I want it to be basically automatically designed. So that's uh, why I was looking at the graph theory algorithms and Steve Skinner, right? So imagine the path. How do you build a building? It might be it's like you think in terms of graph theory. Um, a building is a bunch of uh, nodes, like is a graph, right? And the robots, you have to specify the sequence that the robot will take to put up the building, and then maybe it's like, well, the building's at the bottom. It's like the shortest path to that, and then the shortest path beyond that, and the shortest path beyond that. So right, so it's like the robot goes from here to here, and then from here to here, and then from here to here to here, right? If you're building like like let's say the building is just one long sequence, it gets to here, then the next one is here. But in reality, the building will be a whole bunch of different parts, right? Like paths that can be taken. Now, I want to do something like that even with the building, but then maybe it's not possible. Like, what is the structure of the building in terms of a graph? And then I was thinking, it's like, maybe you should use Prolog when it comes to that. Like, so it's like, where does any particular part go that maybe is a query, right? Uh, so maybe I have a set of queries. Like, let's say if there's a part like this, and there's a part like this, and there's a part like this, what's the next part, right? And that's maybe a pure Prolog query. It's like, you know, th- this part will be late if these conditions are met. This part will be late if these conditions are met. This part will be late if these conditions are met. So you run that over each you start to grow the graph by running each query over that node, and then the next node is that node is created, and then you run all the queries, and the next code is created. So it's like the building is generated that way by running queries over, a bunch of queries specifying that the what is the next thing that will be laid down when given any particular node in the graph. And so that's my thinking on it. It kind of feels a bit like how living creatures grow, right? Like there's a bunch of rules, and then the rules dictate that what is the next addition to the structure of the living organism. And so that way. And yeah, so my hope is like once I've created this animation and all these detailed specifications and algorithms for how the building and the robots collaborate and make and things, and maybe even plans for how to do maintenance on the building and replace the parts, then I can publish this material and maybe get financed for a startup for actually making a building, right? Or maybe as a first step, create a physical system, or get finance for creating a small version of this as a test, and then have it finance for creating a real building and the robots to make it, and so on and on. And different types of buildings or different types of organizations, right? Like, imagine laboratories that do experiments on mice and tissue engineering experiments and things on mice, and then how do you do that? The buildings, and you need to do that. The robots, you need to do that. How to build those robots, how to create the factories that build those robots, all the way down, right? And have that as an animation, and then try to get that financed by doing all this work that demonstrates that you know what you're doing, and you have a literal plan for it, and maybe the fine details need to be worked out, but basically the structure is in place. And if it gets financed with millions of dollars or hundreds of millions, all this goes ahead and is done. Yeah, so I can't remember. I think those were the topics I wanted to discuss today. Um, yeah, so I probably should have a list of things to discuss next time, or try to write lists and then go through them so I can remember what I wanted to say.